Okay, welcome to Adobe Substance Days at GDC. My name is Kat Tamburello, and today I'm going to present to you Building the Dark Fantasy Materials of Doom: The Dark Ages. I want to thank Adobe for having me. I'm really excited to be here and share some of what id Software has been doing. So I've been working in the industry for around 8 years. I started out as an environment artist working on various projects such as Super Nintendo World and some of their AR/VR experiences, WWE 2K20, and God of War Ragnarok. I've been at id Software for around 4 years now. I was initially hired as an environment artist before making my transition over to senior material artist. I'm just going to go over the agenda for today. I'm going to do you a general overview of Doom: The Dark Ages and the technical art team, which was formerly known as the materials team. I'm going to touch on our damage reveal system. Then I'm going to talk about our thought process behind building our material library. Due to our small team size and the scope of Doom: The Dark Ages, we took a modular approach to creating our materials. We made a bunch of filters and generators, and I'm just going to dive into a few of those that I made, such as the material to planks, edge damage, and wood damage filters. Next, I'm going to give a general overview of our composite material pipeline, which is also known as multi-layer blended materials. After that, I want to go over the development of the Dragon and Atlan maps. There were a lot of technical hurdles that we had to overcome when building these maps due to their scale, and I'm going to go over some of the solutions we found for these maps. Lastly, I'm going to do a deep dive into our banner generator. I created this generator in Designer due to the large number of banners we needed for the game. And I'm just one person, so I used every tool at my disposal in order to speed up the process. Doom: The Dark Ages is the single-player action FPS prequel to the critically acclaimed Doom 2016 and Doom Eternal. It was released on May 13th, 2025 on PC, Xbox Series XS, and PlayStation 5 Base and Pro. It was developed in id Tech 8, and some of the key features of Doom: The Dark Ages is that the game had large open worlds for the player to explore, but we also needed to run at 60 FPS. So the materials team was established following the release of Doom Eternal in order to improve productivity and better manage our texture assets. Before the team was formed, materials were made on a case-by-case basis by artists who specialized in other areas. Unfortunately, this approach did not lead to consistent or performant results, so we needed dedicated artists to handle this role. The goal was to ensure adherence to PBR standards and to have a dedicated team to oversee shader development alongside our engine team. The team started out with our lead, Nicholas Clark, who was responsible for creating the vision of what the team would be. Soon after, I joined id Software as an environment artist. However, as the team was in its foundational stages and I had an interest and experience in material art, I transferred to the newly formed materials team. We were struggling there for a couple of years with just the two of us, and then we were lucky enough to add Coraline Liu to our materials team. It has always been a relatively small studio where developers wear many hats, and the materials team is no exception. During the development of Doom: The Dark Ages, the team expanded and broadened its scope into areas requiring additional technical expertise, including vegetation, weather, and gore. With these additional responsibilities, we added our final person, Field Leisner, as our gore artist. So due to these broader responsibilities, the team was reestablished as the technical art team, which better reflects the work we've been doing for much of the past several years. So with that out of the way, I'm just going to share with y'all the trailer for Doom: The Dark Ages.
Our enemy is divided. The time is now. Launch the Slayer.
The Slayer has been activated.
I
right. Thanks. Cinematics team did a great job. So there were a lot of production challenges we needed to solve for Doom: The Dark Ages. Doom: The Dark Ages is a very large game. Not only were the Slayer levels expanded to allow for more exploration, the Dragon and Atlan maps were even larger to accommodate gameplay inside of your giant mech, battling huge serfs, and flying through epic cities on your very own dragon. We also implemented the new damage reveal system. This system allows the player to not only damage surfaces dynamically, but the damage also persists. If the player returns, the damage they created will remain, so the player can have a real impact on the world. But this meant it almost doubled our material library. We also had to quickly build multiple biomes. We needed many different material variants for the same assets so we could use them across all the different maps. So our production needed to be streamlined. We had to think of as many ways as we could to speed up our production process. So for the material team, that meant utilizing the procedural tools at our disposal, such as Substance Designer. So the damage reveal system was developed with the goal of allowing the player to cause damage to the surface of an environment that persists in the world and remains performant. It's a material-based system that dynamically height blends artist-created damage textures into a material surface. It was developed as a more dynamic and lightweight alternative to traditional impact decals. The damage reveal system relies on damage markers, which maintains a list of marker objects such as spheres that can be spawned by different events. This can include projectiles from the player or enemies or destruction pieces colliding with the surface. Damage markers also drive other material effects, such as seamless triplanar blood spills triggered by our AI gore systems, or plasma weapon effects that have an emissive value, creating heat on the ground that slowly dissipates. We couldn't accomplish the look we wanted with generic procedural damage for different surface types, and due to time and performance reasons, we couldn't develop a fully procedural system and engine. So the decision was made to create unique damage reveal for most of our tiling material library. And as I mentioned before, that meant almost doubling our tiling materials. So this would have taken an eternity if we did each one by hand. And as you already heard, we were a very small team and we had a lot on our plate. So we needed to come up with some procedural solutions to build these damage variants. So here you can see a scene with destruction, but without the damage reveal enabled. And this is what the same scene looks like with the damage reveal, and you can see it adds a lot of additional detail. Here we have an image of the damage marker debug view. Each marker tracks its position, orientation, and direction of impact, along with some additional data. Any material surface within a marker's bounds will blend in its corresponding damage variant. This system has many editable properties. For example, here, the Skull Crusher sprayed multiple spheres to replicate the spray of skull shards. If the player threw the shield, it would use a squashed cube to more closely align with the shape of the shield on impact. Or plasma weapons would trigger a glow from heating the surface on impact. All of these parameters can be adjusted in engine. Damage markers also persist throughout the map. And this means that if the player returns to an area they've previously visited, the damage they've inflicted to the environment will remain. So thanks to the hard work done by the rendering team, this system is very efficient, meaning that millions of instances are possible. Lastly, we have the damage mask debug view. So how do we know which regions are damaged? First, a screen space mask is rendered, which determines the amount of damage. Then the damage layer of each pixel's material is blended based on the mask. This blending is additionally modified by the material's height map, as well as some other set material parameters. And I just want to give a huge shout out to our awesome rendering team for all of their hard work. If you want to hear more about damage markers and rendering for Doom: The Dark Ages, go ahead and check out Rip and Tear, Breaking Down the Rendering of Doom: The Dark Ages by Philip Hammer and Dominic Lazarek on Wednesday at 4:30, room 3005 over here in the West Hall. So we had to figure out what tools we could make that would give us the most value. To start, we determined that some common material variants we would need in our library was like tiles, bricks, and planks. Initially, we made a large brick generator that could handle making any type of brick, but this graph was way too cumbersome. It had too many nodes and too many dependencies, so it really slowed down the graph. So we changed our approach, and we realized that different surface types, such as stone, wood, tiles, and bricks, all shared similar damage properties. For example, stone cracks and erodes, wood splinters, tiles shatter. So we switched to a modular approach by creating generators and filters for our Substance Designer library. These filters added versatility and speed. We could create any number of combinations and adjust parameters to suit each specific material's needs. For example, cobblestone might go through an edge damage, a shatter, and my personal favorite that I made, our chunk damage filter. The first materials I'm going to break down is our process for creating wood planks and their respective damage variants. I chose this material in particular because I haven't seen a ton of breakdowns on this online, and it was one of the more complex generators that we had to figure out, so hopefully you guys see something useful in here. So to start, let's dive into the material to planks filter. This filter was designed to take any base wood materials as inputs and create any number of plank variations. The filter has numerous parameters to adjust the look of the planks, such as plank amount, height variation, bending, and warping, as well as some color parameters for staining and light damage. To start the graph, I made a series of textures that I'll use by other nodes throughout the entire graph. We started out with a tile generator grayscale, and then an edge detect with varied thickness, which we blend together using a histogram select as a mask. This makes sure that the gap between all of the planks aren't exactly the same, so it kind of varies up the look. Next, a flood fill to random color and flood fill grayscale mapper with a gradient linear input fed into a histogram scan. The position value is exposed here for our plank bend parameter, which allows us to control how far the bends spread across the planks. I also organized my graph with my generic noises in their own frame so I can use them throughout with the portal node. The portal node is probably one of my favorite features that was added to Designer because I'm a neat freak and it keeps my graph nice and clean, so I don't have a lot of designer spaghetti going on in my graph. We also have the base wood texture inputs, which are then fed into a vector warp random color texture we created earlier. This makes the wood texture varied across each individual plank. Now with the foundation out of the way, I started creating a variety of edge damage using a series of slope blurs, different noise variations, and blend modes. I created 2 variations using a similar node structure that achieved slightly different results. And then I blended those 2 damages together just to add some more variety. From there, I blended our initial plank bend texture and exposed the opacity value to control the bend intensity. A Perlin noise that was vector warped with our random color mask was also blended over top to create an undulating water damage sort of effect over each of the planks at various intensities. I exposed this blend opacity as well to control the warble intensity. And lastly, I created the edge seams using the edge detect, bevel, and slope blur nodes with different noise inputs. As I mentioned earlier, the filter also creates a color texture based on the base wood color input. This allows me to utilize all of the custom grunges and masks used to manipulate the height map inside of the same graph. For example, where there is edge damage, that same mask is used to blend in our damage color parameter. So sometimes we might want to add additional details, so I continued with our modular approach. Here we can input the material to plank outputs into the edge damage filter. So this builds some additional edge damage details. The filter includes a mask output, which can be used to add additional color and gloss information. So this is inside of the edge damage filter. It's pretty small graph, it's very lightweight, and there's 2 different layers of edge damage with their own parameters, such as opacity, intensity, smoothness, scale, and disorder. And it also allows for custom damage inputs and mask inputs. And this filter can be used with either a height map or an edge mask. You're just going to get very different results depending what you input. So now that we're done with our base planks, let's take a look at our wood damage filter. This filter had to be versatile and able to create wood damage for multiple purposes. It had to be able to create damage for either plain wood or wood planks, and also with varying levels of damage from only moderately worn to completely decimated, so we could use it for our damage layers. Like before, this graph has several inputs. We have our base wood textures, our plank pattern, and our plank random grayscale. All of these are outputs from our material to plank nodes. So let's take a look at our damage mask. I start out with a flood fill mapper with a gradient linear. The scale, position, and rotation adjust the results we can get here. And this creates a mask on the ends of the plank shapes as if chunks on the edges of the planks have been ripped out. And our histogram scan position sets our plank damage spread parameter, which determines how far the damage spreads into each individual plank. I also have a tile sampler, which controls our chunk damage parameters. Again, size, spread, and chunk amount are some of our parameters we have exposed here. And then this is fed into a plank switch, so if there are no planks, it will just ignore the flood fill mapper mask. That mask is then fed into some non-uniform directional warps to add some shard-like distortion. And lastly, I put this into a flood fill bounding box size and into a threshold. This parameter is also exposed so that I can remove any extra tiny pixels or tiny chunk shapes that I don't want. This mask is then fed into a bevel, which changes the look of the depth of our plank damage. After that, it's just more slope blurs, multi-directional warp, and non-uniform directional warps, and it adds more of the broken wood shard shapes. Now that the mask is done, we just subtract this damage mask from our height input, and this is sort of like a Boolean operation. Next, I added some additional details. I put the damage mask into a quantize and just overlaid that so it would add some layered wood around the damaged edges. I also multiplied a fiber noise for some more detail. And now that I've booleaned the chunks, I did a min darken of some wood chips to add some minor damage. This is just a linear gradient min darkened over a pyramid shape that I then fed into a splatter node. And then that was put in through some directional warps to add some warble. So now I had to material height blend in these base planks. This is for the most damaged version of any sort of wood plank material that was input. So I just started out with a mega scan and manipulated the color and details to create the proper look that I wanted. These planks also have their own parameters, such as the switch to turn off the bottom planks, underlying color for the planks, as well as a parameter to adjust the surface height for the underlying planks. I wanted to add some debris like sawdust and some large splinters. For the sawdust, I just took some shard shapes and put them into a splatter circular to create some piles. Those were then fed through a shape splatter to create the sawdust in the damaged areas. And I called that damage mask that I made earlier to use as the mask for the sawdust, so that sawdust would only show up in the most damaged areas. And I did the same thing for the large splinters. It was just the individual pieces, and then I didn't use the mask because I wanted them to be able to spray all over the material. So here we have a damaged wood subgraph that we used for the generic damage. It has outputs that were used, like color and some additional height information that's used throughout the graph. It also has 3 inputs: color, height, and an RGBA pack map of the shards. This just cuts down on the required number of inputs, and then I don't need to make the shards again inside of this graph, so it improves performance and it just simplifies the graph. So to make these details, I just use a tile sampler with the wood shards with random scale, position, luminance, and a bit of random rotation. And then that was fed through some non-uniform directional warps. And then I just subtracted this from our initial height input. And then I have a uniform grayscale that's blended with min darken to kind of scrape the top of the surface. And this grayscale value is exposed, so the intensity of the scrape can be adjusted. After that, I wanted to add some termite damage, so I just took a dirt noise through a histogram scan and quantized it, and then multiplied it over the height. Lastly, I overlaid a warped wood megascan for some extra detail. Lastly, I set up the color texture with a uniform color parameter used throughout the graph. I also made a custom color match node, which is basically the same as the out-of-the-box color match node, but I removed a bunch of parameters that I didn't need just to speed up the graph. So just like the wood planks, the wood damage filter also has its own built-in color nodes with various adjustable color parameters for the wood damage areas and the bottom planks and the sawdust. Okay, so that's it for the wood. I hope y'all are still hanging in there. I know that was a lot. But next up, I'm just going to talk about our composite materials, which is also known as multi-layer blended materials. Okay, so how do composite materials work? Composite materials generally consist of a baked macronormal and an RGBA mask. Other maps like albedo, specular, gloss are not required, but you can add them for certain use cases. The RGBA mask controls the material layer blending. Each channel corresponds to an individual tiling material layer. There are some additional parameters that control the blending of each tiling material. Some of the parameters include albedo, gloss, spec, normal, and height scale. Tiling can also be set for each individual layer either uniformly or non-uniformly if necessary. However, most of our assets are using automatic textile density feature, which automatically sets the UV tiling of each material so that if an asset is scaled, it remains with the right textile density. So like I said before, composite assets use the shared tiling material library. This decreases texture memory costs. Assets with composite only need a unique macronormal and RGBA mask texture. Albedo, gloss, spec, normal, and height textures are called from each material layer, but these tiling materials are being used on assets all throughout the map. It also speeds up asset creation. Material variants can be created quickly by swapping material layers. It allows for consistency of materials across the maps because, like I said, they're all using the same shared material library. And it helps maintain textile density, especially on large kit pieces like cliff rocks. So if you scale a cliff rock really big and the macro normal might be under textile density, at least your tiling material layers are going to hold up. So in addition to the standard scale or opacity parameters for color, gloss, spec, and normals, composite materials also have a few height map specific parameters. Height map scale is a multiply for the height input that affects the blending between the layers. As you can see in the image, changing this value modifies how the high and low values of the height map affect the material blend. We have layer scale here, which just affects the overall opacity of the layer. And layer softness controls the fall off of the mask, similar to a contrast setting for the mask itself. Okay, let's take a look at an example asset. This is just a simple cliff rock. So the red channel is generally just defining the base surface of the material. In this case, it's one of our basalt rock materials. This mask is most often white, but if an asset includes more unique maps, it can have a grayscale mask. Our green channel usually just creates variation across the surface, so I just blended in a lighter color rock to add some more breakup. The blue channel is for our occlusion and concave curvature to add in some details in the crevices. In this case, I wanted to create sort of an oxidized effect. And lastly, we have the alpha channel, which uses convex curvature to add wear along the edges. We try to adhere to this standardized procedure for each material layer so that when making a large number of assets for a map, we can achieve consistent results, but sometimes that's just not possible. And here you can just see a couple of map variants with the same rock. We've got some granite, some sandstone, some basalt, and we can just use these across all of our different maps. All right, that's it for the composite materials. Next up, we're going to move on to our Dragon and Atlan maps. Oops. Video doesn't want to play. Well, that's fine. So there were a lot of technical problems we had to solve for the Dragon and Atlan maps. These maps are very, very large in scale, so tiling is obvious with the automatic textile density feature, just due to the sheer size of the assets in the maps. So there was also a lot of space to fill. A lot of the assets needed to be made, so modularity was key here. Additionally, the same tiling materials are used on the Dragon and Atlan assets as well as the Slayer assets. We couldn't create a unique tiling material library just for these maps because it would be way too costly from both a time and performance standpoint. So our proposed solution was Vista hotspots. A hotspot is basically like a trim sheet and an atlas combined, as you'll see soon enough. Hotspots are used throughout the Slayer maps, but these would be unique in that we would set custom tiling inside of these materials to accommodate for our scale. So why use Vista hotspots? It allowed our environment artists to mid-poly model and still have sculpted details. This is a lot like using a trim sheet. It also allowed rapid creation of building variations, and also because our hotspots used the composite material workflow, it alleviated the obvious tiling. And this was a new challenge for the studio. It would have been a lot more difficult to solve this problem without the dedicated materials team because of how much R&D was involved. And the player can actually get pretty close to these assets when they're flying around on the Dragon. So this is just one of the assets from our Dragon map. This was the initial blockout phase with only model details. And then this is the initial blockout of the Vista hotspot applied to the model. Here we have the Vista hotspot without any material layers. And here's the final Vista hotspot setup. Here you can see the difference between disabling and enabling the automatic textile density feature. My video again is not playing, but that's okay. You might be able to see here that there's a little white dot on the screen. So that right there is our scale dude standing next to a window. So maybe that puts the size of this building into perspective. And here's a close-up. Maybe you can see him. So the Vista hotspot had an initial model blocked out, and then I just took it into ZBrush for sculpting. The key here is that I wanted to add as much sculpted detail as possible to create visual interest without adding any sculpted details that were too unique. Unique details in the baked normal would make it obvious that this was a hotspot was repeating across the asset. When making the hotspots, I tried to keep in mind where UV seams would be and built it to tile on itself as much as possible. So for those of you familiar with the wrap mode in ZBrush, you can imagine this was a hassle because these are not exactly one-to-one, so I had to do some finagling, but I think it was worth it in the end. And as I mentioned earlier, our hotspot materials use the composite material workflow. So here you can see some of our composite material mask layers, although it's not playing on your end either. So because we use the composite material workflow, this allowed us to swap out our 4 material layers to quickly create variants that could be used across any of our different maps. Okay, I just want to give a huge shout out to everyone who was involved in creating the Dragon and Atlan maps. Every department had obstacles they had to overcome when making these levels, and it wouldn't have come together without all the hard work from everybody. Special shout out to the environment team for making all of the assets and using the Vista hotspots and building these huge maps. And with this all wrapped up, I'm going to move on to the final section, our banner generator. So this is a snapshot of a banner in the engine and the material in our material editor. Each unique banner starts with an inherited decal, like a parent material, with all the proper textures and baseline bend values. This includes an albedo, RGBA mask, and sometimes a normal map if there is one. The albedo map is set up to rely on our gradient mapping system in the material editor. This works in the same way as gradient mapping in Designer. With this in mind, all of the banners have a grayscale albedo that can be used with a gradient map to create an infinite number of color variations. Additionally, banners are composite materials, which means they receive the same benefits as our Cliff Rock did. All the variants share the same RGBA mask, and material layers can be similar depending on the situation. I just want to shout out to the concept team. They designed a ton of banners, and without them, I wouldn't have been able to create this many variations. So the generator starts out with an imported bitmap with an alpha channel for the initial shape of the banner. The alpha is used inside of Designer to create a custom damage mask to input into the banner generator. I did this inside of Designer instead of an external software because it gives me the flexibility to adjust the banner's damage on the fly. So the banner generator is responsible for creating the RGBA mask for use in the composite material. Inside of the banner generator node, there is a fabric damage subgraph. This subgraph manages the bulk of the banner creation. So to start out in the fabric damage node, I made some tattering at the bottom of our banners. I started with a tile sampler grayscale and stretched a paraboloid that I fed into a slope blur and a non-uniform blur grayscale. This mask was then used in non-uniform directional warp node on our on our mask input. After this, I warped the edges further with a directional warp using a simple directional noise. Lastly, the histogram scan has its position exposed, and this parameter allows me to control how far the tattering moves up the banner. So I also wanted to add holes to the banner. Again, I used a tile sampler grayscale with 2 disks put through a slope blur and a histogram scan. Additionally, I used a gradient linear as our mask input, and the tile sampler node has several exposed parameters such as scale, XY amount, random position, mask random, and mask map threshold. The mask map threshold parameter controls how high up the banner the holes will appear. So earlier in the graph, I created a woven fabric pattern with a series of tile generators and blended them together and then fed them through some directional warps with a wrinkle height map. This means that the fabric damage node can be used to create a normal map if needed, complete with wrinkles and a weave that will follow the direction of the height map. This same pattern is also used later in the graph to blend over the holes, so there are still some threads intact. Additionally, I used the same thread pattern to add hanging threads from the bottom tatters of the banner. And with all of these details combined, we have our final mask output for the banner, and we can adjust any of these parameters to create a variety of looks. So now that we have our final opacity mask, let's just jump back into our banner generator where we created our final RGBA mask. Like our other graphs, we're going to start out by creating a series of masks using the flood fill node that will be used throughout the rest of the graph. Some of these masks include an edge mask, gradient mask, the green channel mask, and an optional blue channel mask. These channel masks are controlled by referencing the banner's input color texture with the color to mask node with all of its parameters exposed. This works kind of like an ID mask, so I control where the green channel layer will appear. Here you can see the green channel mask is multiplied with a dirt noise, clouds, and the fabric damage mask to add some breakup. Our blue channel is just a series of custom grunge maps blended to create a top-down grunge streak pattern for dirt. And lastly, we have our alpha channel, which is also just a series of custom grunge nodes. And then this custom grunge is add sub blended over top of our modified edge mask. This channel accounts for wear around the tattering and holes in the banner that was created by our fabric damage node. And this is our final banner, albedo, alpha, and RGBA mask outputs that are used in Engine to create all of our banners. And with that, that is it for me. Thank you all for listening. I hope you all got something out of it. I want to do a quick shout out to everybody who contributed to Doom the Dark Ages. It's a team effort, and it wouldn't have been possible without all the awesome people I get to work with. And I think we have some time here for Q&A, maybe, possibly. Do we? Yeah, okay. I can't see anything, so I'm not sure where people are at. Hi.
Hello, my name is Alex Ferrix, and I am a junior at DigiPen who studies environment art.
Okay.
I was wondering if you had any tips for, like, with your materials, like, managing, like, storage space or, like, file space or, like, performance, if you had any, like, advice?
Yeah, for performance and kind of maintaining file space, a lot of that is like packing maps, for example, like packing your texture maps and stuff like that. And then like in your graphs, for example, like using as few nodes as possible to achieve your results is going to help speed up your graphs a lot. So those two things, and then keeping in mind like texture size.
Thank you.
Yeah, for sure.
Hi there.
Hello.
My name is Allison. I am from DigiPen. I am an environment artist. When it comes to the compositing,
Sorry, guys, I'm having a hard time hearing everybody's questions.
sorry about that.
You're fine. Where is it coming from? If you wouldn't mind just repeating.
No worries.
Yeah.
Hi there. My name is Allison Knight. I am from DigiPen Institute of Technology. I am a 3D, generally more environment art. When it comes to composite texturing, you mentioned the Atlan masks, are those separate from a bitmap, or excuse me, not bitmap, I'm trying to think what those were.
You're fine.
They are the texture UV, I'm trying to think what it was called when you have all of those maps like specifically in the space and you map them. I forget what it's called. Starts with a T. It's on the tip of my tongue. But anyways, back to Atlan.
Yeah.
What does that mask actually feature, and what are the components of those, would you say?
The components of the composite mask?
Yeah, or even Atlan in that sense, or if it's the same thing.
It's the same thing. So like the masks that we made for the composite materials for like the Atlan maps, it's the same concept, but it's just different because of, what we're using those for. So like for that section, it was about using the Vista hotspots. So those masks were for specifically that Vista hotspot versus using it like on the rocks, which would have like a asset specific mask basically. So that like contributes to all of your different tiling material layers.
Very cool.
Yep.
Alrighty, well, thank you very much.
Yep.
Thank you.
Right.
I was just wondering, we have materials that are using the composite layer to blend the different layers. So let's just say wood, stone, and metal. So if you have like a barrel and then a door that are both using it, are these two different instances, or have you found a way to make it so they all are able to share? Is it like deferred?
It just sort of depends. So the question was, if you have like a prop with wood material and a metal material, would that be one composite material, or would it be multiple materials? Is that the question correct?
Okay. The question is, let's say you have two variations of the same prop. Are these two separate instances of the master material, which has the composites?
Yes, yes. So if you have two different variations of a prop and they're using a composite material, it would use that base master material as its parent material, and then you would change out the tiling blend layers to make different variations.
Okay.
Yeah.
Hello, I'm Justinian. I am a student programmer and designer, so this isn't really my area of expertise, but I like to learn about the different things in order to work better with my teammates. This is less of a technical question, but more of when creating the materials, what like core design pillars and philosophies did you follow with all of them to make sure they all like fit into the game? And how do you really decide like, okay, which things here should have like more procedural elements to that texture versus which things should have just, you know, their own set beginning texture that doesn't really need like a bunch of stuff like the warping or maps or stuff like that and could just be made and implemented?
So when we were kind of figuring out how we were going to make different textures and materials for different assets, a lot of that started out like we would start out making a library per map and determining what materials we would need for that map specifically. So we'd sort of just start there and get all of the base tiling materials we would need. And then after that, it was more just like a case by case basis. But usually once we built out that material library for a map, with the composite material system, we could use those tiling materials to create a lot of different variations for props and things like that that we needed.
Thank you.
Yep.
Hello. Oh, this is really too close. Wow. Hello. My name is Ethan Moore. I'm a student at NYU Tish's game design program, and I make independent games with my siblings, and I've had some experience with Blender designing deal toys. And I have a question about the system you're using for destruction of terrain damage. So I played the previous newer Doom games, huge fan of the series, and I was wondering if this is similar to, or if there's any relation to the previous a sort of enemy destruction system you had in Eternal in 2016, where like enemies would get shot and they'd have like bone exposed and stuff like that.
Yeah, so that's our gore system, and that is, yeah, pretty similar to the older games. I think there was a couple things that were adjusted, kind of like the materials, for example, and how those work with our gore system. But the gore system as a whole basically stayed the same. But the damage reveal system on surfaces was something that was new for Doom the Dark Ages.
Okay, thank you.
Yep.
Hi, I'm Eureka Yulin, and I'm a student of SMU Guildhall, and I'm a material artist. And my question is like, for very large assets that cannot use the modular keys, how do you keep the textural density consistent between the main structure UV and trim elements that use the trim sheet? For example, it's like if both the plank using the wood material and the decoration of a sheep is also use it, how do you maintain a consistent textile density for the base wood surface? Yeah.
Okay, so the question is, how do we make sure that textile density is consistent across different assets that are either using the composite or
Especially trim
sheets in different situations?
Yeah.
So usually that consists of, one, the composite materials have the automatic textile density feature. So the tiling materials have a set textile density in the base composite material that we set ourselves. And so using the automatic textile density feature, if you scale that asset, it will maintain that textile density within each of those layers. But if you create, say, an asset that isn't using the composite material workflow and it just has its own, baked maps and everything like that. It's really just about how you build out your asset. So you just want to be cognizant of your UV scale and making sure that your UVs are matching that textile density when you actually lay them out. And if you need to split it into multiple materials, that's something that you have to consider so that when they're like next to each other, it doesn't look super different, basically.
So it's like I cannot adjust the UV randomly because the trim sheet has already fixed the density of it.
Yeah, so with the trim sheets, those are also using the composite material workflow. So all of our trim sheets also use that same workflow. So they have each individual tiling material layer in there and then the mask in there. So it's just the baked macro normal and then the RGBA mask for the trim sheets.
It's like the structure is one layer and yeah.
Right, yeah. Yep.
Thank you.
Yep.
Hi, my name is Alex Maddox, a producer also from SMU Guildhall back in Dallas. And my question is, as a kind of the newly formed team over the past few years, knowing what you know now, what are some things that you do going forward that you learned specifically making the materials in all advanced new systems?
Yeah, so as a new team, what would we do different than we did when we started? I think a lot of it was when we first started out, we were trying to build just like a huge tiling material library that could accommodate like all sorts of situations. But it kind of turns out like we don't actually need that many tiling materials for the game, and some of them like don't actually get used all that much. So now I think going forward we'll probably just be a lot more intentional about how we're going about what we add to our library. That's definitely something that we're going to do moving forward. So
Perfect, thank you.
yep.
Hi. Oh, shoot. Thank you for the presentation. It was super interesting. So when you're making these complex materials, how do you know how much detail you put in until you just stop? How do you know when a material is fully complete?
How do I know when to stop putting in detail for the materials when I'm making them? That was the question?
Yeah.
Yeah. So usually that's just like a lot of going back and forth. So obviously like I'll be looking at the material in the rendered 3D view inside of Substance Designer. And at a certain point, I'm going to export that into our engine and then go back and forth in the engine and kind of see it more in context. And that's going to give me a really good idea of how it is going to actually look inside of the game. And then a lot of times, I mean, I don't even get to decide really when I'm done, right? Because I have other people making approvals for me. So that decision is often made for me. So yeah.
Awesome. Thank you.
Yep.
I think we're going to stop here.
Cool. Sounds good. All right. Thank you.